Welcome learners to the course on Quantum Electronics Part 2. Myself Orpon Deashi, working in the Department of Electronics and Communication Engineering in RCC Institute of Information Technology, Kolkata, India. Welcome you all to my video lectures, the series of video lectures on quantum electronics. In the lecture 7, I will briefly discuss about the quantum Hall effect. And let me first clear that I won't go to the fractional quantum Hall effect or like those things. I am basically stick to the calculation of the quantum Hall resistance from the profile, and it's a very brief analysis. Nothing more than that. So that portion may be covered a little bit later on if time permits. But today I will be confined in a very small region. So before going to the more details, let me first very briefly explain what quantum Hall effect is. The definition of quantum Hall effect is the phenomenon where resistance of a quantum wave system becomes quantized, and when under the condition of low temperature and high magnetic field. So quantum Hall effect is nothing but the quantization of the Hall resistance under the simultaneous satisfaction of the conditions of lower temperature and higher magnetic field. Let's see how it can be calculated. If you have a quantum wave system, naturally it will have a 2 degrees of freedom. Say I am considering z direction is quantized, or say x direction is quantized, or y direction, whatever. You can say for my calculation I am taking x direction quantized, and y and z, that means yz plane is free for your playing of the carriers. So naturally the parabolic dispersion relation E equals to h cross square k square by 2m, and similarly k can be written as root over ky square plus kz square. I think I am not going into the resolution of vectors for the preliminary things of the school level, so it's quite familiar to all. So the number of energy states per energy interval in real space, that will be kappa square by 2 pi. It's a simple definition. I think if you forgot, go to my lecture 5 where you can get the number of energy states, the calculation from the density of states expression. So it will be kappa square by 2 pi. So I'm substituting that. So what will be the density of states for a particular subband? And you know the calculation, it will be m star by pi h cross square. And at the time I show you that this is the working formula. So once you will get that, then the kinetic energy, you know, in magnetic field the kinetic energy is quantized up to the Landau level. Why? Because you know the familiar with the cyclotron motion, and the Landau level up to that all the energy carriers are filled, so that kinetic energy is filled up to that. So energy separation between two Landau levels, that we have calculated in our earlier magnetism classes, and that is h cross omega c. And you know the omega c is the cyclotron frequency. It will be qb by m star. M star is the effective mass of the electron between the which electron, the electron of the material which exists up to the Landau level. So for that it is the m star. So once we know the kinetic energy and the energy separation, the number of energy states, how you do calculate? It should be density of states multiplied by the total energy range. And what is my total energy range? Between two Landau levels, it is h cross omega c. And my density of states is rho. And what is the value of rho? You know, m star by pi h cross square. Again, please remind. that I am considering a single subband, not all. If you consider all subbands, then the Heaviside step function will come into play. But I am not interested with that because we are going up to a single Landau level where all the energy values are filled. So why we will consider the Heaviside function? It's not at all required. And then I have substituted the value of omega c also, which is qb by m star. And naturally, if you substitute all the values, the number of energy states up to the Landau level will be qb by pi h plus. Simple algebraic calculation. Now Landau level is a fixed value, so you can't consider all the subbands, those formalities. So let ns is the number of carriers up to the Landau level. So or fine, but what will be the definition of the quantum Hall resistance? That will be the definition of Hall resistance is field by Q multiplied by NL. And what is NL? I am showing the previous slide. That is the number of energy states up to the Landau level. So B by Q NL, and you know the value of NL. It is pi h plus by QB. So if you calculate R quantum Hall resistance, that is h by 2q square. Now look at the factor. H is the Planck's constant, which is constant. Q is the electronic charge, which is also constant. So resistance, quantum Hall resistance is a constant quantity. And if I move from one to another, that means if I increase my eigenvalues, the magnetic fields, simple, you will get h by iq square. I is the integer factor. And look how it will be per ohm, that is square per ohm, and how the graph will vary. It will be a pure step functions as we will progress for lower I values. For higher I values, that will be a smooth transition, and corresponding to every step you will get a peak, and peak is your nothing but the sheet resistance. So sheet resistance will give you peak, whereas the Hall resistance will give you the values of the step function. And that's the phenomenological trend, that the graph is one of the most significant graph in the quantum mechanical earlier classes. You may ask, what is the significance here? Now the Landau level below Fermi level are completely filled, and you know the above Fermi level are naturally empty. This is the basic definition of Fermi level. So due to the existence of the impurity and disorder, the sharp Landau levels becomes broader, where I am again showing the graph. Look out the peaks. The peaks are not sharp. These are broadened. So sharp Landau levels are broadened because of the presence of the impurities. And that's why they are called Landau band. If you just recall my lecture 6, I have also stated that energy levels in a quantum well system are not the levels, they are also band. A combination of multiple energy levels. Similarly, Landau level is not in a level, it's a band. And once you are considering the bands, but mind it, these are very closely spaced levels. Then the carriers at the tail of the Landau band are localized. Naturally, if you take a bowl and if you put some particles inside it, all the particles will try to accommodate the space at the bottom of the bowl. So carriers will also try to go to the tail of the Landau band and localized. And when the carriers will be localized, when they don't want to move, naturally you have to lower the kinetic energy of the carriers. And how could you lower the kinetic energy of the carriers? You have to lower the temperature. And also from the graph you will find that the distinct peaks are observed if your magnetic field is high. So now recall your definition, that both lower temperature and higher magnetic field are required to get the quantum Hall resistance, which is a constant quantity, and that's the reason behind it. So if Fermi level lies in localized state, the Hall resistance will remain constant, And that is one of the key finding, that magnetic field and lower temperature has a profound effect on the resistance of the material, that is the sheet resistances, as well as resistance per square ohm. So that's one of the very key finding, and that can be calculated from the knowledge of the density of states. I am not repeating those steps in this video lecture just to keep it short, but if you have problem, go to the derivation of the density of states of quantum well in my lecture 5. Go to my channel and the playlist, you can get the lecture 5, and the derivation is clearly given for a particular sharp band. The value will be m star by pi h cross square, which value I have used it and get the desired result. So thank you all. Up to this is the quantum Hall effect. From the next class onwards, I will go to the calculation of the absorption coefficient and oscillator strength. That means we will move towards the optical properties of the quantum structure. Thank you all.